Okay, we're talking about reaction kinetics and collision theory. Collision theory depends on two things. Number one, it depends on orientation. Orientation has to do with how those molecules bump into each other. And number two, activation energy. The amount of energy required to go and make a reaction take place. Third factor, let's see, high activation energy, go. They must collide with correct orientation, and they must have sufficient activation energy.
Test.
I'll be with you in a second. This picture here shows the difference between a exothermic reaction. Exothermic is going to give off more energy than is required to get it over the hump, in other words. So it takes this much energy to get the reaction going, and then once it happens, you end up down here. So we end up with less energy in the products than we start with in the reactants. That means it's exothermic. It's giving off energy. And the opposite would occur if I had endothermic. Endothermic means it takes more energy from the reactants than what I end up with the products. I end up with more energy in the products, in the bonds that bond those chemicals together, bond those atoms together. And so this is endothermic. The energy is stored in the bonds, and so I end up at a higher level. It still has activation energy though, so it's like lighting a piece of paper on fire. I have to have the match to get the paper start to burn. So the match is here. The match gets it burning, and then it takes off by itself and it keeps going. In fact, burning paper would be this one, okay, because it's exothermic. It's going to give off energy. The products of exothermic reactions are usually simpler than the reactants of exothermic reactions. Okay, now this has to do with spontaneity. Here's your delta G, Gibbs free energy.
Student.
Yes.
You only gave me star student.
I don't even know what star student is. Nobody's ever told me about it. I've been here 4 years. I've never heard about it. I mean, I hear about it, but I don't know what it is. Delta G, Gibbs free energy, indicates whether something is going to be, ready? Spontaneous. So I light a piece of paper on fire, it's spontaneous. It keeps going. I don't need to keep heating it up. I don't need to keep lighting a match, unless it's pouring rain out. That is what Gibbs free energy is used to figure out. So there's a formula in here we're getting to. Okay, maybe we'll fast forward here to section 2. Okay, catalysts, inhibitors, okay? Catalysts make reactions go faster by lowering the activation energy. Let's talk about that in a second. Okay, chemists can change reaction rates by a couple things. Number one, concentration. So what affects reaction rates? Concentration. Higher concentration of reactants, faster they react. Makes sense. You got more of them in the same amount of space. Number two, surface area. How do I make a chemical reaction go faster? Grind up my reactants into smaller pieces or dissolve them so that they're in solutions. If you try and react things that are big chunks, they don't react as easily as if they're small chunks, because smaller chunks, more particles, more collisions. Everything goes back to the collisions. And that has to do with surface area. Okay. Also, third thing, temperature. Reaction rates go faster at higher temperatures, everywhere, any reaction. And usually it's double the rate for every 10 degrees Celsius. Double the rate 2 times for every 10 degrees Celsius. That's just a general rule of thumb. There's no formula. But if you are trying to do your laundry, you want to wash it in what? Hot water, not cold water. Why? Because it cleans a lot better than hot water. Okay? So 100-degree water instead of 50-degree water, or 100-degree water instead of 60-degree water is a lot more effective, because it's going to be 2 times 2 times 2 times 2. 100 versus 60 is 16 times better. 2 times 2 times 2 times 2, right? Yeah, so it's a big deal. Temperature is huge. Because it increases kinetic energy, they're moving faster, they bump into each other, everything goes back to collisions. The more collisions we have, the faster the reaction. Reaction rate and temperature, you can see this one takes off, goes a lot faster at higher temperatures. Okay, and then lastly, a catalyst. Catalysts are things that lower this hump. They actually cut the top off the hump. So a catalyst doesn't react. A catalyst doesn't change the chemical reaction, Ben. Catalyst just lowers the hump of activation energy. Okay? And I'll try and get this out tonight so Sean Tyler and Houston can look at it too. Okay, inhibitor is the opposite of a catalyst. It inhibits instead of makes go faster, it slows it down.
Is an inhibitor like putting something in like an ice bath to like cool it down and slow it down?
Yeah, that would inhibit a reaction, but you're just changing temperature there. So an ice bath would inhibit a reaction, but it's not an inhibitor. An inhibitor is a component that literally keeps the components from bumping into each other. Just like a catalyst makes it easier. I usually, when we get to this chapter in class, I usually talk about a blind date. If somebody sets you up on a blind date, they don't go with you on the date, do they? That would be really awkward, right? That's all a catalyst is. A catalyst says, hey, you, carbon dioxide, come over here and meet nitrogen monoxide. And once they get them together, they don't get involved. So catalysts do not get used up. They do not participate in reactions. They are just there to make things meet each other. In the human body and in living things, they're called enzymes. That's all an enzyme is a living catalyst. Catalysts lower activation energy, and that means they bump into each other more. Okay, heterogeneous catalyst and homogeneous catalyst just has to do with the state, solid, liquid, or gas. Homogeneous means it'd be the same state as what it's catalyzing. So if you have liquid solutions, it'd be a liquid catalyst. A heterogeneous catalyst can be like in your car, in your catalytic converter of your car. You have solid little pellets of palladium, PD, and they react with the gases that come out of your engine to make them react and not pollute the air as much. So that'd be a heterogeneous catalyst. Okay, and we're on section 3. Cool.
Oh, yeah, so that's why they call it catalytic converters.
Catalytic converter. It has a catalyst in it, and they're very expensive. Palladium is expensive stuff. Yeah, but you don't put platinum in a catalytic converter. People will be breaking them open because that's really expensive.
Isn't that called like the noble metals or whatever? Palladium and then gold.
But that's like a
silver and platinum.
That's platinum group, I think.
You got the coinage metals here. Those are called coinage metals. There's a name for those.
Platinum group, I think. Was it?
Yeah, no, there's another ruthenium or rhodium. I can't remember. I don't know. There's a name for it. Okay, number here. Rate law. This is what you need to know. Okay. Rate is equal to a constant times the concentration of a reactant. Okay, now this is going to get more complicated from this point forward. This is the simplest form of this reaction, rate law. Okay, rate is proportional to, we could say, a constant. And it's going to be different for every chemical reaction. And they're only determined, write this down, this K is only determined experimentally. There is no law, you have to literally either do the experiment or look it up in a book of somebody who's done that experiment to figure out what K is. And then A is the concentration, like in molarity, like we're talking about this chapter, of a reactant. Okay?
So you're given K?
Yeah, so again, I can give you K and A and you can calculate the rate. or I can give you the rate and A and you can calculate K, or I can give you rate and K and you can calculate A, okay? I'll show you the units here in a second. I haven't done these in a while. K is the rate constant. Usually it's something like moles per second or molarity per second. So you're changing a concentration that's changing. So your concentration, your rate constant is going to be, if you look at the units here, it'll be the rate, which is per second, divided by concentration, like molarity. Anyways, we'll figure it out here in a second. Okay, some reactions are first order reactions like this one, which just means there's no 2 or 3 or 4 in here. The reaction rate of hydrogen peroxide is a first order reaction. And it's linear. Can you see this right here? So linear just means as the reaction concentration increases, moles per liter, the reaction rate, moles per liter per second. Okay, there's your units. Okay, so let's jot that down. Moles per liter. Where are all my black markers? Oh, I remember. I should throw them in the table. And moles per liter per second. So K, let's see, concentration would be in moles per liter, and reaction rate would be moles per liter second. That's what it looks like. It's hard to read up here. Okay, now if we have a chemical reaction that has reactants and more than one reactant, okay? So here, the general rate law says if I have more than one reactant, I have to get both of them in there. Because if I increase the concentration of one reactant, or both reactants, it's going to change how fast it occurs. So A and B represent concentrations. The exponents are the rate orders. The rate of reaction is equal to the product of K, and the concentration of reactions raised to the power that is determined exponentially. The M and the N are experimental. There is no rule of thumb. There is no law. It doesn't come from the balanced chemical reaction, although a lot of people try to put them in there based on the coefficients. They get confused with something else, which we'll talk about in a few minutes. Okay? So the rate is A, concentration of A to a power M, concentration of B to a power N. If there was a third reactant, it would be concentration of C to the power O, or whatever. Okay, so this is a lot of stuff we do chemistry with. Okay, the negative rate equals, in this case, for this reaction, it would be NO squared times the concentration of H2. And remember, see, it has nothing to do with the coefficients. And we're going to talk about something in a few minutes called an equilibrium constant, which does have something to do with coefficients, but this doesn't. Rate does not. This is determined experimentally, squared and to the first power. And that just explains that there. Experimental reaction rates. You could take this data here and you could calculate, for instance, the rate of reaction for different things. Plug them into that formula. Okay, so we could take stuff like this. Doubling A doubles the reaction rate. That would be a direct relationship, like we talked about in the last lab. If doubling B quadruples the reaction rate, well, that means if I change this number, it's squared. Okay, quadruple.
Wait,
Mm.
so A is doubled and B is quadrupled?
Well, if I double, it says if I change the concentration of A by 2, it's going to double this number over here. If I change the concentration of B by 2, it's going to change this number by a factor of 4. Now, the problem is both of these can change at the same at different rates.
So why does A have like a square and B have a 4?
Because for whatever reaction this is talking about, and it doesn't list one here, that would be the reaction rate mechanism for that reaction. It's determined experimentally.
Okay.
Okay? Why is it? It would have to do with the shape of the molecules. It would have to do with reaction sites, how many different orientations they can bump into each other in. It's just a whole bunch of microscopic variables that
Find that out
influence.
when you do the
It's experimentally determined. They have to give it to you. In other words, they have to
Yeah,
tell you this.
That's,
Yeah.
that's what I was confused on. I thought
Yeah, on a test, there's no way you can determine this except from something. If they tell you this, you can write this. Okay, if you write this, you can say this. So they're showing you here, this is how you describe the rate in terms of this. And if you had experimental data that told you this, you had a graph that said this was linear, and you had a graph that showed this was quadrupling, which is a geometric progression, then you could write this out. And that's how scientists, chemists do that. They do the experiments, they graph the results of change of concentration over time, and they say, oh, it's first order, and we would say this is first order in A and second order in B. That's how you say that, okay? Let's jump ahead here, going real fast, but again, this is chapter 16. You can take a look at some stuff tonight. And that is one more section. Instantaneous reaction rates. I'm not sure what this is. It's been a long, long time since I've looked it over. I wouldn't worry about it too much. Let's go to chapter. This is important. Let's talk about this for a second. Reaction mechanisms and intermediates. Okay, let me show this. Hopefully there's an example here. Okay, chlorine catalyzed decomposition of ozone. Chapter 1 in our book. Okay, here is ozone, O3. Here is a chlorine atom. Okay, so when these things react, you end up with hydrogen chloride, or ClO, and O2. That's what this is showing. How does that happen? Well, it happens in a couple steps. It doesn't really just all happen all at once. First, the ozone decomposes into two parts. Second, the chlorine would react with this to form this, right? Then I got one of those left over. Yeah, I'd have to figure this out. Let's see if I can keep going here. Okay. So a lot of different chemical reactions have steps like that. Everything doesn't happen at once. You have intermediates. Those intermediates form and then break into things almost immediately as they bump into other components. Whoa. And so what is that?
Down.
Down?
Actually, no, those are just the questions, aren't they?
Yeah, it's a big review section. In 70.
No, 47. And 48.
46.
Ooh, look at that. That's cool. So right here, rate determining step, the slowest of those steps. So it's kind of like if you see a multi-car pileup on the highway, right? And all you see is the final picture. You see 6 cars and they're all rearranged like this. Boom, 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 boom. They're all going different directions. How'd that happen? Was it like 6 cars in a row and then all of a sudden, boom? No, it doesn't all happen instantaneously, right? This car bumped into this car. It made it swerve. It made him start to spin. He bumped into that car. That car hit that car and got locked together. Those 2 cars slammed into a pole and bounced off. And then the last car plowed into him. So it happens in steps. Chemistry's like that. There's a sequence of steps that get you to the end products. We usually just write reactants and products, but it's really more complex than that. So in order to figure out how fast the chemical reaction goes, chemists figure out which one is going the slowest. Which one of those steps happens the slowest. And that's going to be the one that limits, kind of like a limiting reactant thing. That's the one that's going to slow down and make things happen the slowest. It's called a rate determining step. Now again, some of this is just theory. There's not a lot of math you can do with this, so I'm going to breeze through this. Where are we at here? This is showing, again, some steps in a chemical reaction. So here's nitrogen monoxide and hydrogen. It goes through an activated complex. It makes an intermediate, N2O2, plus hydrogen. It goes through another activated complex and makes another intermediate, N2O plus H2O plus H2. And then over here, goes through another activated complex, and then my final products are nitrogen and water. So if we're writing out this reaction, what are we going to say? We're going to say NO plus H2 produces N2 plus H2O. This is my reactants, and here's my products. But in real life, it does a bunch of other things in between. Okay? And those are called activated complexes, intermediate complexes. There's energy for each of those associated. And whichever one of these goes slowest is the one that's going to control the reaction. Let's see if we can get to, yeah, and so we're at the end of chapter 15. Let's take a look at 16.
That is 16.
Really? Let's back up to 15 then. Which I think is, let's see what we got here. Okay, 15, energy, heat, I still missed Gibbs. Thermochemical, okay, that's where I missed it. Reaction spontaneity is the Gibbs. Okay, 15, here we go. Some of this is review, okay, conservation of energy, joules, calories, heat, specific heat. I'm going to breeze through this real quick. Energy, review, potential, kinetic, conservation of energy, we all know that. Chemical potential energy, like in a battery. Like in batteries are the most famous kind of chemical potential energy, but also in food that we eat, that's chemical potential energy. Fire, when we burn logs, that's chemical potential energy. Oil, when we burn it in our cars, or gasoline, chemical potential energy. Methane gas, propane gas, anything we explode, anything we burn, chemical potential energy, okay? Lots of stuff. Heat, what's the symbol for heat? Let me look back here. Q. Q is heat, write it down. Small q, by the way. Calorie is a measure of energy. We use it when we talk about food a lot. And sometimes the food that we eat is called kilocalories, by the way. So if you eat a 100-calorie bar, 100-calorie protein bar, it's actually 100 kilocalories in science. Even though on the wrapper it says 100 calories, capital C. Usually that is right here, capital C. Capital C for a calorie in food is 1,000 small calories or kilocalories. Joule is what we use in science, guys, and you can transfer calories to joules and joules to calories.
Do you think we'll need that on the?
It might be on there. Does anybody have a copy? I have, once I give you, here's my folder, by the way, if you want to take home, if you haven't printed it out yet. Take one of these copies home with you tonight, because I don't need them, but bring them back to me. I'll keep them for next year. But if you want to glance through that, this is just the last year's one. Look at the front page where all the conversions are. I think they probably have calorie on there. Let's find out. They got pressure. They got specific heat of water.
I don't see calorie.
No, I don't see
Celsius,
calorie.
centi, and Coulomb.
Coulomb. That's electricity. Interesting.
What is the number for calories?
It's on this chart right here. This is the most easiest one. The most easiest one. This is the easiest one to remember. It's 4.184 joules per calorie. And the reason I say that is this is a famous number as well, because 4.184 is also the specific heat of water. 4.184 joules per calorie, and you'll see in a minute it's 4,184 joules per kilogram is the specific heat of water. Well, go figure, same number. So water, again, is tied into our energy system, just like 0 Celsius and 100 Celsius, boiling and freezing point. Water is tied into everything we do. Okay, specific heat, here we go. Specific heat is the amount of energy used to raise a temperature by 1 degree Celsius. It's different for every substance, but here's water. You see the one at the top? 4.184 joules per gram, not joules per calorie. Okay? It's different for ethanol, water as a solid, that's ice, water as a gas, beryllium. But notice how big the number for water is. Right? We've been talking about that in our basic chemistry class. What makes water special? Huge. This thing absorbs heat very slowly, holds heat, and that's what gives us weather on Earth. That's what gives us climate. That's what gives us humidity. That's what controls and makes our Earth a lovely place to live. Specific heat. Here's the formula for specific heat. Q, amount of heat transferred, equals C. This C is this number back here. So C is specific heat. Now when I learned it, we used to call it C sub P. I don't know why, but it was also always CP. I don't know why, but C is not the speed of light here, it's specific heat. Times the mass in grams, times the delta T, or change in temperature in Celsius. So if I give you, again, any 3 of these 4 variables, you can calculate. You can calculate Q if I give you C, M, and delta T. You can calculate C if I give you Q, M, and delta T. You can calculate M if I give you Q, C, and delta T. Or you can calculate delta T if I give you Q, C, and M. Make sense? So this is in grams. This is in deltas Celsius minus Celsius. Change in Celsius. This is going to be in grams. Joules per gram per degree C. Notice that the grams cancel out, the Celsius cancels out, and then joules. So energy in joules. Everything works out. So the key to remembering this, that's a conversion factor. Key to remembering your specific heat is the units here. Joules per gram per degree Celsius. And that is given to you right there for water. Everybody see that one? 4.184 joules. And instead of per gram, they write gram to the -1, Kelvin to the -1. Now they put in Kelvin, and guess what? It's the same number. Why? Because I'm taking a delta. Remember I mentioned this a week or 2 ago? Yeah, we did some of this. If I'm taking a delta, where's the formula? Hey Houston.
Hi.
If I take a delta temperature, whether it's 100 Celsius minus 50 Celsius, or whether it's 373 Kelvin minus 323 Kelvin, guess what the number's going to be?
Same.
50, okay? So both of these numbers are going to be feet. As long as this is a delta, I can do it in Kelvin or in Celsius. So the specific heat, okay, this one's in Celsius, and Houston, we're just looking at the number that's given for water on the chart here is in Kelvin, joules per Celsius, per Kelvin, per gram. You can take one of these home if you want. Okay, we're working through chapter 15, Houston. We just went through chapter 16. And I'm video recording it, so don't bump that chair next to you, and if you want to watch some of this tonight, you can, okay? Section 2, chapter 15. Our goal is to get to Gibbs free energy. It's in this chapter, trust me. Okay, thermochemistry. Whoops. Energy in chemical reactions is determined using a calorimeter, hence the word calorie. Everybody see the word calorie in there? Which means what? Thermal energy, heat energy. A bomb calorimeter is a device. It looks like a super insulated jug like this, okay? And in the middle, it has a thermometer, and you can put water and control the temperature very accurately. And so if I put something into there and either make it react or put something in there at a different temperature, depending on the change in temperature of the water that's inside the calorimeter, I can in fact calculate what the specific heat in joules per gram per degree Celsius is of that substance, or I can calculate other things, how much thermal energy is. Okay? So this is actually used to measure C value, the specific heat value of something. It could be water, it could be alcohol, it could be ammonia, it could be chlorine, anything we put in there. Okay, thermal chemistry deals with thermo, energy, that's all it means. System is always specified as what we're talking about. Anytime we talk about energy, we have to specify our system so we know what energy coming in, energy going out. Surroundings is everything except the system. The universe is the system plus the surroundings. Enthalpy, keyword. You'll see it, don't get confused. It's just heat. Enthalpy is heat. It's usually delta H. You'll see this a lot in a second. Enthalpy is heat content. So if you have a swimming pool, and in the middle of the summer it's 80 degrees, it has a lot of enthalpy. It has a lot of delta H in it. If you have a swimming pool, the exact same swimming pool in the middle of the winter, and it's at 50 degrees, the enthalpy would be a lot less.
Hey, can you post the notes for this chapter to the portal? Because since I wasn't here on Monday, I don't have them. And
You can watch the video too.
other
I
videos
posted
in
it
the-
last
okay.
night.
Awesome. Thank
Okay.
you.
But I'll try and remember to do that. Enthalpy, heat of reaction, is the change in enthalpy during a reaction. It's shown by delta H sub Rxn. Rxn stands for, everybody? Rxn? Reaction. Yeah, okay, it's an abbreviation for reaction. Really tricky, really tricky. Okay, so delta H, how do we calculate that? It's going to be the final enthalpy minus the initial enthalpy. How do we calculate that? Okay. It's going to be the enthalpy of the products minus the enthalpy of the reactants. Ta-da! How do we calculate that? Okay, we're going to get there. So, enthalpy of a reaction is products minus reactants. For exothermic, it's always going to be negative. For endothermic, it's always going to be positive. This just shows enthalpy changes. So if I have something that's exothermic, my reactants start here, my products end up down here. If it's endothermic, they're going to be switched. It's going to absorb heat instead of giving off heat. And we show the delta H. Notice the format here. Delta H is shown as a negative number if it's exothermic, in kilojoules. Or it could be joules, but usually it's in kilojoules because it's a pretty big amount. And if it's endothermic, it's going to be a positive number of kilojoules. Here's a positive one, for instance, plus 27. And I start with my reactants here. I finish with my reactants here. Enthalpy has increased, so they've absorbed energy, right, to go from reactants to products. And so I have a positive 27 kilojoules in this case. Okay, enthalpy of combustion is the same as enthalpy of reaction. Don't sweat it. We just have a combustion reaction. Thermochemical equation is a chemical reaction that has kilojoules with it. I'll show you one here in a second. Okay. Here's some typical heats of combustion or enthalpies of combustion. So if I burn sugar, if I burn gasoline, if I burn simple sugar, if I burn propane, if I burn methane, these are hugely exothermic. So big, huge numbers here. Negative 5,000 kilojoules per mole of stuff that I burn. These are huge numbers. You want to figure out which one of these we were talking about the other day, remember? What's the best fuel? Is it going to be this, or is it going to be gasoline or diesel or whatever? I forget what we were talking about. So we were looking at this. What's the delta H of combustion? It's called a heat of combustion or an enthalpy of combustion. Those are determined experimentally in a what? Bomb calorimeter. It has nothing to do with a bomb. Don't worry about it. Okay. Molar enthalpy of vaporization. So I turn something into a gas. It takes a certain amount of energy to do that. So we have an enthalpy to change things into gases. We have an enthalpy to change things into solids. We have enthalpy of vaporization, enthalpy of condensation, enthalpy of fusion. okay, sometimes called heat of fusion. All of these are delta H's. Fusion, there it is. Molar enthalpy of fusion. How much does it take to melt something? Here's some examples again. How much energy to change water into gas? How much energy to change water into ice? Or ice into water? No, water and ice. I think these ones would be negative. No, that's positive. That's going to be endothermic. And this would be to change ice into water. It gives off energy. No, it absorbs energy. Yes, both of those are fine. As long as we define fusion, sometimes is melting and sometimes fusion is freezing. I always get confused. Yes, sir.
So the 3 letters under the H are just, they don't actually affect their
Vaporization, fusion, combustion, COMB, reaction, RXN.
So it's basically just telling you what you're doing, really.
It's just the change in energy from start to finish, or finish minus start. Okay? So just talking about energy here. The word enthalpy is just change in heat energy, which is Q. And remember, Q equals mCp delta T, or mC delta T. Phase changes of water, blah, blah, blah. Combustion, food. Okay, next. Cram a lot in here. Okay, Hess's law has to do with adding together steps in a chemical reaction. Like, we talked about, a chemical reaction can occur in other small pieces, those intermediate steps. We can then take a total reaction and calculate the total reaction energy from the steps reaction energy. And here's an example, for instance. If I want to make sulfur trioxide, which is SO3, right? I have to take S plus O2, and I have to change them into SO2. I have to react SO2 with oxygen to make SO3. There's an intermediate step. And so the first step has a certain energy associated with it. The second step has a certain energy associated with it. So guess what? How much is the total energy going to take? That plus that. If we balance them. Okay? So we need to make sure that this reaction, this plus this equals this, and this reaction, this plus this equals this, balance out to the final reaction, which would be, let's see if we can do it here real quick. Sulfur plus oxygen produces SO3 is what we're trying to get to, right? So 3, 2, 2. Yep, that's what they got. Oh, they don't have 3 oxygens, so that's a problem. Oh, they do. Okay. So I have 2 oxygens here, 2 moles of oxygen here, and a 3rd mole of oxygen picked up here. So there is 3 moles of oxygen. And 2 moles of sulfur I start with. These we don't worry about because they get formed and then used up. The SO2 gets formed here and gets used up here. And so my final reaction is there. Standard enthalpy of formation. Quick word about this. Number 1, enthalpies of formation. So where do I get these numbers from? Okay, let's go back here. So if I want to make sulfur trioxide, it comes from sulfur and oxygen, right? Standard enthalpy of formation defined by the change in enthalpy that accompanies formation of 1 mole of a compound is, in its standard form, is from its elements in their standard states. So elements in their standard states have a delta H of 0. In other words, if I'm making plain sulfur, sulfur in its natural form found in nature has a delta H of 0. Because it's the simplest thing you can get. We're not reacting with anything just by itself. And oxygen, known as O2, in its simplest state has a delta H of 0. Now that's a weird one. And let's talk about that for a minute. I need to double check. I'm doubting myself on that one. So let's look at this for a second. Okay. Delta HF is heat of formation or enthalpy of formation. And we're going to do it for all of the products and add them up. Then we're going to do it for all the reactants and add them up. And then remember, we take products minus reactants, and we get our delta H of reaction. You leave it?
Yeah. Sorry.
That's okay.
Do you still want this, or do you want me?
If you want to look through it tonight, you're welcome to. If you don't feel like you're going to use it tonight, then just leave it here so it doesn't get lost. There, just plop it on my desk there.
So,
I'm looking at the O2. The O2 here, they've got a 3 halves O2, which is 1 oxygen atom. Yeah, see you tomorrow, Andrew.
Bye, Steve.
Let me know how it goes.
Okay.
Hmm?
Bye, Will. Bye, Dick.
see you.
Bye, Andrew.
I have a question.
Mm-hmm.
This is kind of random. We're looking at the equations, and what is E? Like the first one.
I don't know what any of those equations are for. So let's just not worry about them tomorrow, okay? Forgive me, I'm sorry guys, but I mean, I could figure it out if I dug out some of my old textbooks, my PChem textbook there and stuff. I don't. It looks like R, I would guess, is the ideal gas law constant. T would be temperature in Kelvin. N is number of moles. Letter F,
F is Faraday.
that's Faraday's constant according to the list above, yeah. And Q is usually internal energy. No, they say reaction quotient. What was
There's
that?
two F's on the
So
constant.
you're looking for electromotive force.
Ah,
What is E to the O?
yeah, that's probably the base. Usually a 0 exponent that refers to a base state or a standard state, something in its lowest energy condition. Just like in the next one, you see the delta H, that's enthalpy. I'm guessing a formation is listed up above. Let's see, delta H.
No, I don't think it gives you delta.
Enthalpy is capital H always, so that's an enthalpy of something. Again, R and T, gas law and constant, temperature. The K we'll come up to in a minute, I believe, is an equilibrium constant. Yeah, sorry. Some things I don't use a lot. Don't use it, you lose it. Okay. Spontaneous, you ready? Write down the word spontaneous. Spontaneous are things that happen once they start, they occur without intervention. So again, if I light a piece of paper on paper, if I light a piece of paper on fire, it's spontaneous, right? Say yes.
Yes.
Okay, if I light a match to a balloon filled with hydrogen gas, it's going to explode, right? Okay, those are spontaneous things. But if I want to bake a cake, I have to stick it in the oven and keep heating it up for half an hour, right? Not spontaneous. If I want to cook some soup, I need to put it on the stove and keep heating it for an hour. Not spontaneous. Some reactions are not spontaneous. You have to keep working them. Spontaneous means once it starts, it's over that activation energy curve. Boom, it's going to keep going. So this is related to entropy, okay? Entropy is a measure of possible ways that energy can be distributed. It's a measure of randomness. And entropy is always going to decrease or increase. Entropy increases by itself. It's the second law of thermodynamics. There's some pictures here showing that if I put two different gases and attach them in the middle with a valve, and I open the valve, what's going to happen? Diffusion, right? Remember diffusion? Why does diffusion happen? It's just random bouncing of atoms off of each other. Eventually I'll end up with some over here or some over here. That's not going to happen. I'm going to end up with some on both sides. You know, they're going to mix like this. I'll end up with some weird, that's a weird picture. I'm not sure what. Second law of thermodynamics is entropy. Entropy is delta S, by the way. Disorder, entropy. There's a lot of stuff here. Okay, let's back up here for a second before we do that. Okay, in nature, change in entropy tends to be positive. That means things are getting more disordered. Think of a tree. A tree in the woods, when it's alive, is orderly. The cells are functioning. They're all rigid. They have nice cell walls. It pumps water in. It grows leaves. It's very, very ordered. When a tree dies, what happens? Tips over, starts to rot away. The cells start to break down. The carbon starts to break down. The wood, the cellulose starts to break down. It becomes more random. It becomes more disordered. So, entropy is always increasing in nature, in the universe. The process is usually exothermic, which raises the temperature of surroundings. So when a tree breaks down, it gives off energy to its surroundings. It does. We don't see that. It's not a huge amount of energy. We're not burning it, but burning it would also increase entropy. Okay, free energy is the energy that's available to do work. And here's where Gibbs free energy comes in, okay? Gibbs free energy is delta G. Delta G is the change in heat energy of a system, or thermal energy of a system, minus the temperature times the change in entropy. So here's your formula for Gibbs, finally. Okay? This is thermal, and this is temperature times entropy. And this comes from the second law of thermodynamics, which says, let's see if I can remember it.
What do you got?
No, it's U equals Q plus W. U, hang on a second. Equals Q plus W. And Q is usually defined as delta H. Okay, so this is the internal energy of a system is equal to the work done by a system and the change. No, that's not right. The total energy of a system. Internal energy. Internal energy plus work equals total energy. I think it's something like that. Anyways, I need to look it up in my thermodynamics book. But that is the root second law of thermodynamics equation, which gives us this eventually. Change in temperature minus temperature times change in entropy equals, tells us whether something's going to be spontaneous or not. I'm going to use this. Does that say that? Okay, let's talk about it for a second.
So that's
If the sign of the delta G is positive, the reaction will be non-spontaneous. If delta G is negative, it is spontaneous, okay? And if you look in the textbook, in this chapter, chapter 15 or whatever this is, yeah, you will find some problems to work. What's it going to give you? Watch. It's going to give me this number, a temperature, and an entropy. And I just put it into this equation. Are we given this equation, everybody? Nope. Thank you.
You said positive is spontaneous and negative.
Yeah. Negative would be spontaneous. If you remember one of them, you don't need to remember the other one. Negative, spontaneous. I always remember this one. Negative means spontaneous. Positive would be the other one, non-spontaneous. The entropy of the universe always increases in spontaneous reactions. And here's a cool chart. Cool. Again, so depending on temperatures of a chemical reaction, they could be spontaneous in some reactions, in some situations where the temperature is at a certain level.
We're in here till 5:30, whenever
I'll be over in about 20 minutes. And they could be spontaneous at low temperatures, or they could be never spontaneous, or they could be always spontaneous. Again, it depends on delta H, delta S, delta G, okay? So, and it goes back to this reaction here. And that's about the end of chapter 15. Okay.
You just ran a marathon.
Yeah, I know. There's another chapter you should probably take a look at too. It's called Equilibrium Constants. Let's see if I can find it real quick. So that's 15 and 16. Those would be key. We'll get to them this quarter, but we're just not there yet. Acids and bases, chapter 18 would be good to look over, but we don't have time. Chapter 17 is equilibrium. Let's look at that for just 1 second. I want to show you one equation, if I can find it here quick. Chapter 17, 15, 16, 17. You guys are in good shape next month. You say, I remember this. You may not understand it, but you say, I remember it. Okay, what is equilibrium? Equilibrium is reversible reactions. So if you've seen this maybe before where you get the double-sided arrow, that means a chemical reaction goes forward and it goes backwards. Now here's the tricky part. You ready? At the same time. So at the same time these are making this is breaking down into this. And this happens a lot in chemical reactions. We can force it to go forward, or we can force it to go backwards by doing certain things. And there's a word for that called chemical equilibrium, obviously. Okay, here is the rate constant. You ready? So if we just start a chemical reaction, we leave it on. Not every chemical reaction does this. Some just go forward, okay? But not some chemical reactions reach equilibrium. So here's how you calculate it. Formula. KEQ. This is a famous constant called the equilibrium constant. For a chemical reaction, depends on, ready? The concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. Now you see how this looks a lot like the rate equation we talked about half an hour ago? The rate equation does not depend on coefficients, and this one does. And that's why people get these two really confused. See, the exponents A, B, C, and D are the coefficients. In a rate equation, they have nothing to do with coefficients. In a rate equation, you have to determine them experimentally. In an equilibrium expression, they do depend on coefficients. And when we get to the final exam or the semester exam, everybody messes this up. Because they do a rate equation problem and they'll use the coefficients. Because everybody always thinks the little exponents are the coefficients. This one's easy to remember. Oh, see, so I have a, let's write an equation. Let's do water. Where's mine? Yeah, H2 plus O2 produces H2O. And if it did, this is spontaneous by the way, and so there's no equilibrium here, but if it was an equilibrium expression, okay, we've got 2 H's, 1 O2, and 2 H2Os. So our KEQ is what it's called, equilibrium constant, equals the concentration of water raised to the 1 power divided by the concentration of hydrogen squared times the concentration of oxygen to the 1 power.
But so why is water to the 1 power? There's the coefficient.
Oh, you're right. 2, sorry, my bad.
So,
Thanks, man.
Thank you.
Okay.
Thank you.
It's on you guys.
I'm dizzy now. So they could give you a problem where it gives you concentrations and you plug them in, or it can give you the KEQ and give you 2 of these and ask you to calculate the 3rd one, or it could ask you questions like, okay, if I increase the concentration of hydrogen, is this reaction going to go forward or reverse?
Have a good day.
Thank you, Meg. So there's a couple things that push reactions in certain directions. Concentration is one. So if I increase the concentration of a reactant, it's going to push it forward. If I decrease the concentration of a reactant, it's going to pull it backwards. If I increase the concentration of the product, it's going to push it backwards. If I decrease the concentration, how do I do that? I just keep bleeding off the product. This is how they make stuff in a factory, right? You want to make something and it's an equilibrium reaction, and you realize it's going to stop. Once something reaches equilibrium, it kind of stops. It's like, hey, nothing's happening. Well, something's happening. It's just going both directions at the same time. How do I make it make this? I start bleeding off the product, and the concentration goes down, and those things are going to keep reacting and producing more product because it wants to get it back to equilibrium. That is called, ready, Le Chatelier's principle. You need to know him. Le Chatelier. Le Chatelier's principle says, if I put a stress on that system, it will force that chemical reaction to either go forward or backwards. The stresses can be any number of things. I think they're probably here. Let's see if I can find them. The stresses on a system. Here's some data, for instance, on concentrations. You need to plug in and calculate the KEQ, like they did over here. Okay. Let me find the Chatelier. Here, the Chatelier. Okay, 1888, he says if a stress is applied to a system, it shifts. And there are a couple stresses. Number 1, concentration. Number 2, pressure. Only if there's gases. Pressure doesn't affect solids or liquids, right? Because they're incompressible. But it's like in this one, if I have gases over here and this is a liquid, let's assume for the sake of argument this was a liquid, then increasing the pressure where I'm doing this reaction is going to force this to go forward because it's going to affect these gases but not the liquid. If I decrease the pressure, it's going to make it go that way. So we always look at the number of moles of gas. There will be 3 moles of gas here and no moles of gas over here if this is a liquid. So pressure. Third one. Volume, which is related to pressure. And that's only going to affect gases as well. And it has to do with the number of moles of gases. Temperature, fourth one. So we got concentration, pressure and volume related to gases, temperature. So if something's exothermic versus endothermic and I increase the temperature, it's going to affect the reaction two different ways. Let's assume this one is exothermic, which it is, and I increase the temperature. Is that going to make it go faster or slower?
Slower, because it'll.
Yeah, I need to think about that one. And it has to do with activation energy. So activation energy, if I decrease the temperature, is that going to lower the activation energy or increase the activation energy? If I increase the temperature, that means the reactants are at a higher temperature, which means activation energy is lower. It's going to speed it up. That makes sense. Hotter reactants, faster reaction. In the forward direction. But if it's endothermic, it's going to be completely different. So changes in temperature alter equilibrium. Temperature changes here. So here is something that is exothermic. Heat is on the right-hand side. Here is something that is endothermic. Heat is on the left-hand side. Right? So if I raise the temperature over here, it's going to force it to go forward. This is the easiest way to think about it. If I have exothermic and I raise the temperature, it's going to slow it down. It's going to force it to try and go backwards. This is a good thing to take a picture of. You want to take a picture? That's cool. This is a good little way to think about exo and endo and how they affect equilibrium. Can you see that, Ben? Okay, catalysts change equilibrium constants, and they can force things to go forwards or backwards. No, they don't, actually. Yeah, it reaches equilibrium more quickly, but the overall equilibrium does not shift, because catalysts, remember, catalysts lower the activation energy, but that's not going to affect equilibrium. Equilibrium is going to be unaffected by catalysts. That's a key point. It gets to equilibrium faster, but it stays at equilibrium the same way. Solubility, we could keep going for another hour. And acids, bases, and electrochemistry is what we didn't get to. Good luck. It's for fun. Just remember, it's for fun. Don't stress. Don't stay up till 2 a.m. Just go and have fun and do your best. Okay?
That was a whole lot of knowledge.